Okay, let's talk about exposure assessment. Actually, the main scheme of risk assessment is clearly the main issue in these days. And actually, what we are going to do now is just to focus on a specific part of this, which is exposure assessment. Exposure assessment, you see, obviously is a critical part of the whole process of risk assessment, in which then you start from the part of research, you focus on which biomarkers, on which mechanism, and then there is this critical issue before moving towards risk management characterization. That's, you have to be sure that there is an exposure before you can try to assess, to think about a risk and how to manage a risk. This is the very critical part. And so what is the purpose? What are the aim of exposure assessment? Actually, definitely establish what's the kind of contact between the pollutants, the agents which is investigated, and the person, and possibly establish the dose. And I will tell you a little bit more in detail in the next slides. And obviously, another critical issue is to define what is the population exposed, who is exposed. And I mean, I try also to think these lessons, thinking about also your problem. So you have an exposure, you have maybe a population which is exposed, and then how to perform this process. So that's the approach was very practical, oriented towards, you have to use these tools. And so identify the population which is exposed, the size, the characteristics of the population, and then use a number of tools, a number of disciplines to perform the assessment, which is not only biochemistry, but also, I mean, geology, atmospheric science, environmental science, even statistics and epidemiology to identify properly the extent of exposure. So there is a number of steps that characterize exposure assessment, which in turn is, I mean, if I have to define it generally, is a multidisciplinary task assessing who is exposed at what extent. So that's to oversimplify the process. And now let's see a little bit more in detail how to perform this assessment. Obviously, there is a number of steps. The very first steps is that we are dealing with what? So the first is physical properties of the agents that we are investigating, and how is transport, how is accumulate into the environment and to the tissue. Is it transformed or does it act as a directly? And in a way, the main question is to address, these are the main questions to be addressed, referring to the characterization of the agent. And this helps in understanding the dose and the route of exposure, obviously. And for instance, in your case, if you are dealing with just with radioactive, I mean, the exposure is to radioactive agents in a way, there's a lot of literature. We know a lot about that and about the kind of the source, the doses, and the route of transmission of exposure. Once this has been done, once we know we are dealing with these agents, then what is the source of these agents into the area that we are investigating? So, I mean, the physical, apart the physical and chemical properties, how is transport, how is it accumulated into the environment? And again, this facts helps to identify to define the dose and to define the route of exposure, which are actually the critical issues in a way. You have to say, you have a population, you have to identify which population, but what is the extent of exposure and where the exposure comes from. These are really critical issues, and so is the identification of the pathways. So once you know the agents and the route of exposure, you have to identify the, I mean, just to make an example, contamination of water sources. I mean, in that cases, exposure can go through drinking water, so food or inhalation. I mean, there is a number of possible routes that must be investigated, and this is the step. And the final step is to measure the concentration. So how much of these agents through this route of exposure reach the body, reach the humans, and at which concentration. So this is clearly a long process. And along this process, there is a number of, I mean, obviously, I don't want to scare you, but I oversimplified something which is quite complicated. And already before you have heard something about those, and even those, and you have to decide what kind of dose you want to measure. And there are several possible ways of measuring the dose of the agents reaching the body, from potential, applied, absorbed. I mean, I will not enter into the detail. You have the slides, so you can go through that. And measuring the dose which is accumulated is a way, and but also an approach in which, I mean, you remember that we have been talking in the first lecture we had on epidemiology, we are talking about bias. And measuring the dose, after you have decided which dose you want to measure, is actually there is a lot of potential for biases. I mean, to measuring the dose in the wrong way, to provide wrong results. And I just make a couple of examples. And because of the bias, that maybe you choose the wrong population, or you choose the wrong way of measuring the dose. There is a number of potential errors that are to be considered, and in particular when you measure the exposure and in terms of dose. One, you can make differential or non-differential errors. And the real error that should scare you is the differential error, which is the way in which the two populations that generally you, in these cases, you investigated one exposed population and you compare this population with a control, which is unexposed. So to see the effect, to compare the two populations. When you introduce a bias in measuring the dose, it means that there are several biases. Think about one is investigator bias. For instance, people that in the area which is exposed pay more attention and make sampling with more attention or for a longer period of different ways. In this case, so the doses in the two groups are not comparable. And this is a real bias in which you overestimate or underestimate the effect of the exposure. Another potential error is the non-differential. In this case, is a little better, because that means that the error that you are making may be because you have a tool for measuring the doses which is not appropriate, is the same in the two populations, in the exposed and the unexposed. So in this case, the effect is the weakening the association, because the precision of your estimation is lower. So generally, there is a tendency to lower the risk. So you know that. So but however, in a way, it's something which is more doable because it does not change your data. There is other interesting issues. One is, for instance, what is called the Bergson bias. That's a typical bias when you say, for instance, if you have to compare, I mean, a population drinking a lot in Europe, maybe, I can't remember. I believe that Czech Republic is one of, there's nobody from Czech Republic, so I can blame them for that. And so you assume that everybody living in Czech is a heavy drinker, which is not true, because the same it happens when in a polluted area, you attribute to each people living in that area the same level of exposure. And you don't know data, you apply this assumption that in many cases can be wrong. Too late, which is wrong. So measurement errors are something that are really critical, because, okay, there is a number of processes I showed you before, but whenever you introduce an error, maybe that your assessment is wrong. And so that's that's a problem. And how can you I say, how can you put all this information together in some simple ways? Or there are, I mean, several ways of synthesizing all this information that comes from exposure assessment. And I found an example, just to give an example, which is from the US Labor Office. This is mostly occupational, but in a way it gives you an idea that you can put together things like the condition, the disease that is claimed, the different exposure that are investigated a priori, and the type of exposure, the route of exposure, the intensity, frequency. And I give you an example, which is, for instance, in this case, there is a claim for people occupationally exposed to asbestos, cement, silica, welding fumes, for the risk of COPD, chronic obstructive pulmonary diseases. Then there is where there's facilities, the dates, the type of exposure, direct or direct as a bystander, route of exposure, intensity, and obviously you have to categorize the wall of information. I mean, quite often a procedure is to transform a concentration in a semi-quantitative value, low, medium, high. Very low, very medium, doesn't work. Medium, high, very high. So in a way, this could be also useful for you in a way, in your example. Perhaps you may want to identify a number of parameters that you want to estimate for exposure assessment, and then to synthesize these parameters in some preformed schedules. Well, that was just a very general, a brief introduction to a general approach to exposure assessment. I would like to focus a little bit the rest of my presentation on the use of biomarkers for exposure assessment. And this is what is commonly done. I mean, nowadays, toxicology, environmental sciences cannot stay without biomarkers, because obviously I believe that most of you are working with different kind of biomarkers, and they provide the use of biomarkers is provide I mean, can confirm the exposure in a quantitative way, often what is called the target dose. Because once you know quite well the mechanism, you can measure how much of the agents, how much of the exposure actually reach the target. So it's a real danger. Where is the danger? And there is a number. You can use it for screening. You can use for biomonitoring. I mean, you can use also biomarker susceptibility. I mean, there is a number of issues. Again, you can read it, but you probably know already, that justify the use of biomarkers for exposure assessment. And think about an example, maybe, I mean, this is a classical approach in which you have the pollution into the environment, then transportation towards the humans exposed, external contact, internal dose, biological, blah, blah, blah. So up to the clinical disease. So these different steps may be relevant for exposure assessment, because you may be interested in, and we will focus on that, on exposure, just to say, okay, you are exposed to something, or you may be interested in the effect of this exposure. And this is really critical in an extended process of exposure assessment. For instance, you can use, you can measure polycyclic aromatic hydrocarbons in the environment, or you can measure it in the plasma. For instance, the measure cotinine in the plasma if you are a smoker. And so you can move from typical exposure marker, in which only the presence, the concentration of the agents as it's evaluated, to something more detailed. In this case, for instance, the formation of DNA adduct by benzoylpyrene or any other kind of polycyclic hydrocarbons, and up to the tissues. And again, also, for instance, benzoylpyrene and other polycyclic hydrocarbons needs activation, enzyme activation. So this process can be used for measuring susceptibility to this particular agent. So you see, this is a little view, and a little more precise view of this process comes from this slide, which has been published by a working group of OECD, that I will say something more in detail. However, the process from exposure to health effect is a long process. It's a long process, is full of relevant events that may be really useful to measure, to quantify. And in general, however, the general idea is to stratify in something more dealing with exposure, and some part more dealing with the effect of exposure. So, and this is obviously is the process leading to the effect. And then there is a number of issues that may be the presence of mechanism, the adverse outcome pathway, to reconstruct the mechanisms linking actually exposure to the effect. And so performing exposure assessment process is to have quite clear in your mind or from literature what is the specific pathway for that specific agent. We know we have an agent, and what is the metabolic life of this agent, how is transformed, what is the impact on the human bodies, and what are the early transformation, and how this early transformation brings actually to the early stages of the disease. This is a little bit more complicated than just to say, okay, what's the concentration of PIH in the body, in the plasma? But is what you should do if you really are dealing with risk assessments. And however, just to make things a little more simpler, otherwise it seems, there are, when you are wanted to assess an exposure to a chemical, at the end of the story, everything falls into the big categories. You can choose, what is it, a level of chemical agents, their metabolites in the body, which is really a marker of exposure, because you just measure the agents that you want to investigate. Or you can measure the biological response to these agents. And that, in a way, is generally very well correlated with the exposure. So you can measure the exposure through biomarker of exposure. And when I say biomarkers of exposure, I mean what I said before. I mean just the levels of chemical agents, the metabolites and or derivatives in cells, tissues, body fluids, or excreta. When we talk about pure biomarker of exposure, we talk about that. Or we are also interested in measuring the impact, the biological response to the presence of this compound in the body. And these are actually the biomarkers of effect. And we will spend a little more time in this on this category of biomarkers. They are called also biomarkers of biological response. And okay, this is can occur can be measurement can be from biochemistry, from molecular biology, or even from bioinformatics, just to say. And this is really critical because, in a way, biomarkers of effect, and I will show you some example now, is really in the middle of the process. When I show you before, there is a exposure, then a long way to the disease. And the biomarkers of effect, in a way, they stay in the middle because that's the idea. I mean, they are associated with exposure, but they also can predict the disease. So that's really important because when you make an exposure assessment, even if you are not an epidemiologist or a clinician, you really want to have an idea of what is the fate of these changes. And biomarkers of effect. There's a few examples from clinics that I want to show because I found really interesting. My favorite example is cholesterol. Cholesterol is a real biomarker of exposure because it's associated with, apart from genetic profile, but is associated with diet, particular diet in which we have an overload of fats and I mean, you know, I mean, you don't know, but when you will be a little older, that you have to deal with your cholesterol, you discover everything about cholesterol. But cholesterol is interesting because it started from an experimental biomarker, but then was validated as a predictor of cardiovascular diseases. So cholesterol is a good example of a biomarker of effect because it's associated both with exposure and with the disease because we measure cholesterol to prevent cardiovascular diseases. The same is for a number of other biomarkers. Think about glycemia for diabetes or the platelet count is a predictor of hemorrhagic events or problems with coagulation states, the iron levels for anemia, liver function, and it's got GPT, the same, or I mean, the creatinine is a predictor of function, of kidney function as well. So in a way, you see that there is a great interest from clinical medicine to biomarkers of effect, and they are part of our lives. We measure often. Most of them are measured in our normal clinics. The point is that that would be great if you can use the biomarkers that we use in toxicology for genotoxicology's assessment on this perspective to predict diseases. So it can be really used for that purpose. And that's maybe possible. And let's move one moment towards this kind of biomarkers that we use generally in The father of all biomarkers are chromosomal aberrations. Chromosomal aberrations, you split the cell in the metaphases, you look how many chromosomes are broken and how they are broken and rearranged. So that's really a very interesting results. And some of these damages are really associated with some important exposure. These cures that you see are dosimetric cures of chromosomal aberration and dicentric chromosomal aberration in particular, with exposure to ionizing radiation. So you see there is a very perfect curve linking the level of damage in the level of damage expressed in gray or in millisieverts, depends, I mean, the level of exposure to ionizing radiation and the frequency, the frequency of chromosomal aberration damages. So that was commonly used when there is, for instance, accident, and just you know, you have so many dicentric. When was the putative exposure? Then you can place that level on the curve and reconstruct the exposure. It works very well. You know, the problem with these biomarkers is that when you have to measure, for instance, dicentric, you have to measure maybe 500 metaphases, because is a rare event, dicentrics. So it means that you have to spend, one person has to stay 1 day scoring the chromosomes just to do one person. So we don't have a real software for automated scoring for chromosomal aberrations. Then that's a problem for which nobody is using any more chromosomal aberrations. Much more popular is finally micronuclei. Micronuclei, that is a sort of biomarker that is absolutely associated with chromosomal aberration, because the idea, micronuclei is a sort of second replication effect of an effect of a chromosomal aberration is second replication. So you have a break in the chromosomes, you lose a whole chromosome or a piece of chromosomes. When there is a new mitosis in the daughter cells, you have one daughter cells with some kind of damages. One damage may be the formation of one small nuclei. I assume you are not familiar with micronuclei, or you are? Some are not. Okay, excellent. And however, I mean, so the formation of this nuclei, which is scored, generally 1,000 cells are scored. There are some ways, for instance, one approach is cytokinase is blocked. The idea, you avoid, when a cell divide, they using the cytochalasin that remain in the same cytoplasma. So that's a sort of cytoplasma with two nuclei, so you can store the presence of nuclei, micronuclei, very well. But there is also other damages, the formation of nuclear buds, the formation of nucleoplasmic bridges, so some chromatin filaments in between the two nuclei, or vacuolization. I mean, there's a number of events that provide, I mean, it's extremely informative, this kind of biomarkers. And there's a biomarker in general of DNA damage, genomic instability, oxidative damage, and so it's, and I was quite, I don't want to spend time in this part, very mechanistic. You can see in the slides, but there is a number of genetic damages that can be measured by the micronuclei, including DNA repair inhibitors, DNA breaks, oxidative damage, blah, blah, blah. And you can have, at the end of the story, a number of endpoints that can measure these events. I wanted to give you an example, because I think that, okay, example are, there are many. I took just one paper from the literature. That was one paper that was published in Colombia in different mines activity. So they investigated the effect on some communities living in some area. I thought that was appropriate for the course, and in which they investigated resident population and workers, miners, in 3 different mines in Colombia, located in different areas of Colombia. And I found it interesting because they measured a number of heavy metals, which is one of the kind of agents which are relevant to this kind of work. And they measured also micronuclei in the population. And they found interesting results. First, there was 3 different areas. This is one typical approach. You remember what I said in my first lessons, that when you do epidemiology, environmental epidemiology, you look things like the trend, the risk is changing a long time, so something that was happening, or geographic clustering of events. So in this case, for instance, there are different mines, but it's quite clear that one of these are more affected by exposure to heavy metals, which are associated more with in this area. And they measured also micronuclei in these groups, in this population, and they found generally, this is the total population level of micronuclei. They're around 4.6 per thousand, 4.4, 5.5, 5.9 per, and this was the 1.4 was the frequency in the referent population. So that means that the frequency of micronuclei in these people is more or less maybe more than 3 times higher than the referent population. So that means something. We will see, because one of the big challenges here is to move from one increase to one effect. So this increase, what does it mean in terms of effect, final effect on humans, in terms of diseases especially? This is really a critical issue, because we measure this damage in people which are healthy, and maybe they develop a disease in 20 years. So the point is that can we say that this kind of damage is associated with a damage, with a disease that will occur in 10 years or in 30 years? That is one of the challenges and of micronuclei. There is another biomarkers which is very commonly used for this very same purpose, and which is the Comet assay. And I'm a little embarrassed to talk about Comet assay. Amaya, don't close your, don't listen, because obviously, you know, I'm not really a biologist, so I'm not doing Comet assay. I'm playing with data coming from Comet assay. And however, the idea is that Comet assay is provides a kind of information which is really similar to that one provided by micronuclei. In a way, if you think about the process moving from exposure to disease, Comet assay, which measure essentially DNA single-strand breaks and a few other kind of events, it's earlier. It happens earlier in a way, that the damages that we can observe with the Comet assay may result in chromosome damage, chromosome instability, and genomic instability, and all the events that are in it. I mean, you see, when I say that we have the possibility to open a hole, open a window in different parts of this process is exactly what biomarkers are doing. How can we say that one biomarker is associated with a disease? It's a very critical issue that at the end of the story, the only way is to perform a cohort study, which is a bias-proof approach. You have people healthy, not affected by any disease, or any critical disease, major disease. Then you measure the extent of chromosome damage or DNA damage. Then you follow them up. After maybe 10, 20 years, you check if the people with the disease are more damages to DNA. That's what we did with the H-Comet project. And these are the results published, in which, I mean, results are highly significant, but I would consider them preliminary anyhow, in which it's quite clear that people with a higher level of chromosome DNA damage have a lower probability of surviving. So that makes sense, because obviously we have mechanisms demonstrated that DNA damage is associated to many diseases. But this is a way in which we can demonstrate this association. And when we talk about this kind of biomarkers, we have a problem, which is the invasiveness. Sometimes you are to take blood, for instance, that may be a problem. And because especially when you deal with people with psychiatric disabilities, or especially with children, because taking blood from children may be always. My wife, she's a pediatrician. I've been once in her clinics to take. You have two people keeping the children or the child. Terrible. Forget blood and battle micronucleus. Battle micronuclei cytometry is another is essentially the same biomarkers, but is measured in exfoliated battle cells, which are much more simple for population studies, even for adults. So you don't have to. There's a number of advantages that unfortunately, I don't have time to talk to you. But essentially, what I said before about micronuclei and lymphocytes is pretty much the same of what you can assume for micronuclei in battle exfoliated cells. Here, an example for a recent is, I believe it is under publication or just submitted paper on a project in Italy in comethicene and air pollution. And it was quite clear they took a large sample, 1,000 children in the primary schools, and they measured exposure to air pollution, and they did two measurements in winter and summer, and they found quite clear validation of the results, quite clear effect differentiating the winter from summer, and especially a good dose-related effect associated with air pollution. So PM 2.5 and other marker of air pollution, which is in a way there is a gradient from North Italy to South, was reflected in the comet assay. So this is also a good example of how you can use this biomarker. And a final point. No, this is not a final point, okay, but I have 3 minutes, okay. And I will escape this part. And I wanted just to finish summarizing what is really the critical issue of this lecture. You can decide if you want to use a biomarker of effect or a biomarker of exposure, or both, which is generally is recommended. And however, when you talk about biomarker exposure, I told you that's the presence of the substance in the body. But there are a number of advantages, which is you have a direct measurement of the dose because of the agents. You measure the agents actually. You don't have to go through biological filters. You measure that. It's very specific. Exposure to PIH, you measure PIH actually. Timing. So you can reconstruct the timing of exposure. So there's a number of quantification, how much. That's a number of very good reasons for choosing this kind of approach. And of course, data are short-term because generally they are excreted. The limited health impact information. You know that you have been exposed, but if all the agent is excreted, no effect on the health. So this is one point. The other point is that you can use biomarker of effect. I show you a couple of them. In this case, you have an health impact insight, which is maybe very relevant. Or you can measure long-term exposure or integrated response. For instance, think about mixture, exposure to mixtures, which is normal to nowadays. So these kind of biomarkers are poorly specific. And this is one of the limitations, and a lot of complexity in the interpretation, but they provide you a lot of information. And the last slide that is really dealing with the use of the two biomarkers that I got from ChatGPT, that was very nice, is that each biomarker has advantages and disadvantages, but they have a specific purposes. And so they use the idea of using the in exposure assessment process, both to use a set of biomarkers, because seldom there is just one biomarker that then tells you everything. And generally, to have a set of biomarkers, a battery of biomarkers is wise once you have money to pay for that. And so in this case, to have biomarker of exposure, good mix of biomarker of exposure and biomarker of effect is a very good idea. That's it. Thank you very much.